in a totally different direction. This was actually work largely done by Cosmo, who you saw in the OpenCog tutorial, and Matt Iklé, with some help by and Belayneh and other folks on the OpenCog team. But this was a snapshot of some ongoing work aimed at getting cognitive synergy, one of the core concepts of the OpenCog architecture, to actually work usefully in practice, which of course is difficult in a different way than conceiving the idea and writing about it. So we have a number of components inside OpenCog. One is PLN, a fairly general probabilistic logic engine, which sort of works now for various types of queries. It doesn't work with the full generality that the theory provides. There's also economic attention allocation, which spreads importance values around between OpenCog's nodes and links, somewhat like spreading of activation in an attractor neural network. And there's a theoretical notion that the spreading of importance through the network should be able to guide logical inference, forward and backward chaining inference, in a way that dampens the combinatorial explosion that comes along with both forward and backward chaining. And we've been playing around with a bunch of examples, trying to get that to actually work and exploring where it works and where it doesn't work. So we've been looking at some test examples that came out of the Markov Logic Networks literature, just to have something interesting to compare it to in terms of another system. I mean, a very trivial example that everyone uses to demonstrate MLN algorithms is given by these predicates at the bottom. Basically, you're given information. Some people smoke, some people don't. Some people are friends with smokers. Smokers will get cancer. People who are friends with smokers are a little more likely to get cancer through secondhand smoke. And then it's just supposed to resolve these various propositions and figure out who's more likely to have cancer, who's less likely, who's totally unlikely, based on who smokes and who's friends with smokers. And I mean, PLN can solve this just as MLN can solve this. It's not very complicated. Attention allocation is not very useful for helping PLN to solve this any better. And the reason why is one of these totally obvious in hindsight things, which is that all the information there is actually useful for solving the problem. And all the MLN test cases we found are like that. I mean, they build test cases where the information in the test case is actually useful for estimating the probabilities you want for the answer. And so knowing what to ignore and what not to ignore is going to be at most slightly useful there. So to make test cases where this attention spreading actually helps PLN, what we're experimenting with now is adding extraneous information. So as well as knowing that Anna smokes, or Anna is friends with the guy who smokes, we also fill up the Anna space with junk like Anna eats cheese. Cheese is very tasty. Cheese is made of milk. And this junk information in there, of course we know it's junk, but the PLN backward and forward chainer don't necessarily know that is junk, so it can spend a lot of time sifting through extraneous relationships and using the importance spreading to focus PLN on certain nodes and links and not others, based on the ones with higher short-term importance values, can then focus PLN's attention on where it's useful and where it isn't useful to do inference. And we're experimenting with that now and tuning various parameters of economic attention allocation to try to get good data on how much ECAN speeds up PLN in this context, which is why it's a position paper instead of a regular conference paper. So probably within a month or two of now, we'll have nice solid results on this, but it's work in progress. But the conceptual point here is, by working through these simple examples, it became more solid in our minds that where the attention spreading really helps inference is where you have junk in your memory which is not relevant to the problem ahead. And of course, a real AGI system usually has that, because most of your memory is not relevant to whatever little problem you're solving at a given point in time. But most of the test problems used for logic systems don't have that, because they're sculpted to test reasoning using the information provided in the file, which is relevant to deriving the conclusion ahead. So that's my 5 minutes on that topic.